Okay, so these are going to be a bunch of short lectures to grasp some basic concepts, um, pretty general about phase transitions, structural phase transitions, in fact, and how to treat them phenomenologically. So, of course, our focus is ferroelectrics, but that's kind of a particular case in a sense of what we are going to do. It's going to be quite unconventional, so you are not going to find these things in a textbook, and it's focused on being able to think about the problems, so that eventually you can think about problems of your own by yourselves. Okay? So I'm not going to pay much attention to formal definitions or to justify in every step. Everything is going to be introduced quite phenomenologically. All right? So the first thing I want to do is to motivate why phase transitions occur at all, phase transitions under temperature variations. And we are going to be working all the time with a very simple model crystal, which has, I'm always going to draw it like this, and always going to draw it in one column. Okay, so it has two atoms in the unit cell. You can imagine it's periodically repeated. In the context of ferroelectrics, this could be a lead atom, this could be an oxygen atom, something like that, but that's not very important for us. Okay, so we have this little crystal in this square unit cell, and we are going to hypothesize that for some reason, essentially because of chemistry, because this oxygen atom in the middle wants to form bonds of a certain length with those lead atoms, this oxygen atom is going to have a tendency to move outside the center of this square. Okay, so actually this is kind of what we will call later the high symmetry structure for this material, but the material reduces its energy by distorting or getting away from this high symmetry structure. So actually the material would rather to be like this, okay, where the bonds between the oxygen atom, the circular atom, and the crosses are shorter, and maybe that optimizes their interactions, etc., as we could compute from quantum mechanics. Right? But then, of course, this is not the only possibility we have to make those shorter bonds, right? At least we have another one. We are going to pay attention to only another one, which is this one. So here I have moved the central atom up, but the central atom could also move down. Okay, so we have two possibilities. Now, if these are the lowest energy configurations of the system, we can be pretty sure that at low temperature, we will find the system either in this one or in this one. At low temperature, the system doesn't have, or let's say in a classical view, these atoms don't have any kinetic energy, so they don't have vibrations, don't vibrate. So they get stuck either in this configuration or in this configuration. Okay. Now, as we heat up the system, essentially two things happen. One thing that is very intuitive is that when we heat up the system, well, the atoms start to vibrate. So in particular, this one, we can imagine that this atom starts rattling. The bond length starts changing a little bit, or at least there is still a favorite bond length, of course, but it starts lengthening in average. Okay? And at some point, it may happen that the temperature is high enough for this atom to be able to break these bonds and to jump to this configuration. Okay, for a high enough temperature. So at high enough temperatures, we may have a situation where from time to time, the atom jumps from there to there. Okay. So at high enough temperatures, if we look at this system, we may have the impression that in average, if we look at it for long enough, or if this jumping happens fast enough compared to how fast we can look, in average, the system is in this configuration. Okay. Now, if I try to be a bit quantitative about this, we could think about the following. We can introduce a variable that quantifies this distortion, right? I can introduce a variable that I'm going to call P, such that P, this variable, is equal to 0 for this state. Okay, P is going to be essentially is going to measure how much the central atom moves off center. I'm calling it P because this will be the polarization essentially. From that point of view, it's more convenient to think by the way that the central atom is positive, so that when it moves up, P is positive and all that. Again, not very important. Okay, so here let's say that P, since the central atom has moved up in average, in this state P is positive, and in this state P is negative. Simple enough, right? So in this scenario, if at low temperature I get stuck in either this state or this state, and at high temperature eventually the atoms can jump between the two, and in average they are like here, then if we were to plot P as a function of temperature, starting from 0, there must be some temperature, so we start, let's say, at a non-zero value of P. In fact, to be more complete, there are two possible non-zero values of P at low temperature. But eventually, if we follow this polarization for this particular system that starts there at low temperature, we would realize that at some point the polarization goes down, and beyond some temperature, the polarization is 0. Okay, this much we can say that the system will do. Okay? And here we have a region that we can call transition region. We may not know exactly how the polarization becomes 0. Maybe it becomes 0 abruptly, maybe it becomes 0 continuously, but certainly over here at low temperatures the polarization is finite, and at high temperatures the polarization goes to 0. Okay? And if we prepare a state at low temperature that starts with a negative polarization, we get exactly the equivalent situation, right? Okay, so because of this mechanism, so with simple chemistry, this happens in many systems. Atoms have preferred interatomic distances, and so we can assume that this, why not, could perfectly well be the lowest energy configuration of a particular crystal. Usually there is more than one possible lowest energy configuration. One is like this, the other one is like that. They are obviously equivalent by symmetry. We'll talk about that a bit more in a second. Okay, so at low temperatures we can have something like that, but as we heat up, atoms can start to move, things can start getting disordered, and we can have this kind of situations. So a phase transition, from this point of view, is a very natural thing to happen. Now, this picture of phase transition by an atom hopping around is the one that most traditionally is presented, and the one that you will find in many places, but it's not the only argument I can give you to justify a transition as a function of temperature. So I want to give you at least another argument. Also has to do with temperature, but this is slightly different in nature. So imagine simply that we start again with our crystal in the low temperature configuration. In the low temperature configuration, this crystal has that structure that minimizes the energy. And as I heat up, we have already seen that atoms are going to start to vibrate. This atom will start vibrating, and these atoms as well will start vibrating. Okay? So an inevitable consequence of this is that somehow the atoms effectively occupied more volume as we increase the temperature. This can be taken as pretty much a general rule. Vibrations will become stronger, and the atoms, if we think about the effective volume occupied by the atoms, certainly it will grow with temperature. So these guys, imagine, now occupy a volume like this, volume like this, volume like this. and this one also occupies more volume. So even if at 0 Kelvin this distance is the preferred distance, as I heat up, these atoms cannot really be at this distance because they will be essentially colliding against each other. Of course, this is simplification. The collision is never going to happen. But it's never going to happen because this atom actually is going to progressively get stuck in the center. Okay? So you see how this is different. In one picture, I was telling you that because of temperature, this atom may be able to jump around. This actually can happen. Another thing that will happen simultaneously, and it's not clear which one is going to dominate, both are going to happen simultaneously, maybe in one system, certain systems, this will be the picture that explains the behavior. In another system, this will be the picture that explains the behavior. Because another thing that happens simultaneously is that the atoms occupy more, and therefore, in the particular case of our example, we have a natural driving force for the central atom to go back to the center. Okay, so this concludes the first bit. Simple phenomenological argument of why we have a structural phase transition.